Hello everyone, I'm Akash, founder and director of Prime Minister of Mathematics, Amravati. In today's video, we will discuss the solution of an interesting question from IIT JAM 2023 Mathematics exam. This question I have posted on our YouTube community post on 20th of this month. Question belongs to the linear algebra and question is, which of the following is a subspace of real vector space R3? And the options are, option A is set of xyz belongs to R3 such that y plus z whole square plus 2x minus 3y whole square equals to 0. Option B is set of order triplets xyz belongs to R3 such that second coordinate belongs to rational number. Option C is set of xyz belongs to R3 such that product of their last two coordinates, that is second and third coordinate, is 0. And option D is set of xyz belongs to R3 such that x plus 2y minus 3z plus 1 equals to 0. So let's begin the solution. We will verify one by one options. So let's begin with option B first. Okay. Let's denote the set in option B by B. That is, B equals to set of order triplets xyz belongs to R3 such that y belongs to rational number. Okay. Now, clearly this set is not closed with respect to scalar multiplication. Clearly, B is not closed with respect to scalar multiplication in R3. To see this, for example, 0, 1, 0 belongs to B. We can see that this element belongs to B because for an order triplet to be in B, we must have their second coordinate belongs to rational number. And here we can see that 1 belongs to rational number. So 0, 1, 0 belongs to B. But for pi belongs to real number, we have pi times 0, 1, 0, which is equals to 0 pi 0 does not belongs to B. Okay, because for element to be in a B, we must have second coordinate belongs to rational number, but here second coordinate is pi, which belongs to irrational number, so it does not belongs to rational number. So the coordinate 0 pi, so the order triplet 0 pi 0 does not belongs to B. And this shows that B is not closed with respect to the scalar multiplication in R3, and hence it is not a subspace of R3. And this shows that B is not subspace of R3. Therefore, option B is discarded. Okay, that is option B is incorrect. Now, let's verify option C. Let denote the set in option C by C. That is, C equals to set of x, y, z belongs to R3 such that product of second and third coordinate, that is y into z, equals to 0. Then clearly C is not closed with respect to vector addition in R3. Okay, C is not closed with respect to vector addition in R3. To see this, for example, (1, 2, 0) and 1, 0, 2 both belongs to C. Why? Because for order triplet to be in C, we must have product of second and third coordinate equals to 0. Here product of second and third coordinate is 0, so this order triplet belongs to C. Similarly for this, here product of second and third coordinate is 0, so this triplet belongs to C. But their addition, that is 1 to 0 plus 1 0 2, which is equals to 2 2 and 2, that is order triplet 2 2 2, does not belongs to C. Why? Because for order triplet to be in C, we must have product of second and third coordinate is 0. Here product of second and third coordinate is 4, not equals to 0. So this order triplet does not belongs to C, and so from here we see that C is not closed with respect to vector addition in R3, and this shows that C is not a subspace of R3, because we know that a subspace is itself a vector space under the same binary operation as that of vector space. So subspace must be closed with respect to vector addition. Subspace must be closed with respect to scalar multiplication as well. So here in option C, we see that the set in C, option C, is not closed with respect to vector addition. So it is not a subspace of R3. So option C is also discarded. And in the B, we have seen that the set in option B is not closed with respect to scalar multiplication in R3. So option B is discarded. Okay. Now let's verify option D first. As subspace is itself a vector space under the same binary operation as that of vector space. So subspace must contains 0 element with respect to vector addition. And we know that the 0 element with respect to vector addition is 0 0 0. And if we denote this set by D, then we can clearly see that this element does not belongs to D. Because if this element belongs to D, then this element must satisfy this condition. And clearly we can see that 0 plus 2 times 0 minus 3 times 0 plus 1 is equals to 1, not equals to 0. So this element does not satisfy this condition. So this element does not belongs to D, and so D does not contains identity with respect to vector addition. So D cannot be a subspace. This implies D is not a subspace of R3, because subspace must contains 0 element, that is identity with respect to vector addition. So option D is also discarded. So we only left with option A, and which is the answer. But we have to prove that it is a subspace of a real vector space R3. So let's prove it. Now we will show that A is a subspace of real vector space R3. For this, we will use the subspace test. It states that let V be a vector space over a field F and W is a non-empty subset of V, then W is a subspace of V if and only if W is closed with respect to vector addition, that is W1 plus W belongs to W for every W1 comma W2 belongs to W. And second, W is closed with respect to scalar multiplication, that is alpha times W belongs to W for every alpha belongs to field F and for every W belongs to W. Okay, we will use this test to show that A is a subspace of vector space R3. So to show A is subspace of R3. Okay. Now we need to show that x1 y1 z1 plus x2 y2 z2, which is x1 plus x2 y1 plus y2 z1 plus z2 belongs to A, and alpha times x y z, which is equals to alpha x alpha y and alpha z belongs to A for every x1, y1, z1, comma x2, y2, z2, comma x, y, z belongs to A, and for every scalar alpha belongs to A. Okay, that is to show that A is a subspace of R3. We need to show that A is closed with respect to vector addition. That is, sum of these two vectors in A, that is this element, belongs to A, and A is closed with respect to scalar multiplication. That is alpha times xyz, which is nothing but the element alpha x, comma alpha y, comma alpha z. That is, this triplet belongs to A. Okay, so let's verify it. That is, A is closed with respect to vector addition or not, and A is closed with respect to scalar multiplication or not. Okay, now this element belongs to A if it satisfies this condition by definition of A, because any element that belongs to A satisfies this condition. Now, for this element to be belongs to A, it must satisfy this condition. So we consider what is this condition? Second coordinate plus third coordinate square. Second coordinate plus third coordinate square. What is second coordinate of this element? y1 plus y2. What is third coordinate? z1 plus z2 and its square plus 2 times first coordinate minus 3 times second coordinate whole square. So 2 times first coordinate x1 plus x2 minus 3 times second coordinate y1 plus y2 whole square. Okay, we have considered this term and we have to examine whether this term is equals to 0 or not. If this sum equals to 0, then this element belongs to A, and so A will be closed with respect to vector addition. Okay, now let's solve this. This sum can be rewritten as, since this is just additions of real numbers, so I can write this sum as y1 plus z1 plus y2 plus z2 whole square, plus I can write this as 2x1 minus 3y1 plus 2x2 minus 3y2 whole square. Okay, now let's expand this term. What we get? A square plus b square plus 2 times a into b. So y1 plus z1 whole square plus y2 plus z2 whole square plus 2 times a into b, that is y1 plus z1 into y2 plus z2. So this is an expansion of first term, plus now expansion of second term. A square plus b square plus 2 times a into b. So a square is what? 2x1 minus 3y1 whole square plus b square is what? 2x2 minus 3y2 whole square plus 2 times a into b, that is 2x1 minus 3y1 into 2x2 minus 3y2. Okay, now we have to check whether this sum equals to 0 or not. Okay, because if this sum equals to 0, then this sum equals to 0, and this sum equals to 0, then this element belongs to A, and so A will be closed with respect to vector addition. Now, okay, now let's see that as x1 y1 z1 and x2 y2 z2 belongs to A, that is, these two elements belongs to A, so these two elements must satisfy this condition, because any element which belongs to A satisfies this condition. So as x1 y1 z1 belongs to A, this implies, as x1 y1 z1 belongs to A, so this implies second coordinate plus third coordinate square, that is y1 plus z1 whole square plus 2x1 minus 3y1 whole square equals to 0. Okay, because this element belongs to A, so this element must satisfy this condition, that is y1 plus z1 whole square plus 2x1 minus 3y1 whole square equals to 0, and as x2, y2, z2 also belongs to A, so this element also satisfies this condition, that is y2 plus z2 whole square plus 2x2 minus 3y2 whole square equals to 0. Let's give these two equations be equation star. Okay, that these two equation, okay, this equation and this equation. Okay, I have denoted combinedly these two equation by equation star, and we will use equation star in this. Okay, so we see that y1 plus z1 whole square, that is this term, plus 2x1 minus 3y1 whole square, that is 2x1 minus 3y1 whole square, this term, sum of these two terms is 0. Similarly, y2 plus z2 whole square, that is this term, okay, plus 2x2 minus 3y2 whole square, that is this term, that is sum of these two terms, y2 plus z2 whole square and 2x2 minus 3y2 whole square is 0. So what will remain? 2 times this 2 will become 0 and this 2 will become 0. Okay, so what will remain? 2 times y1 plus z1 into y2 plus z2, okay, plus 2 times 2x1 minus 3y1 into 2x2 minus 3y2. Okay, give this as equation hash. Okay, now we will again use equation star. Okay, now from first equation of equation star, we have star implies first equation of using the first equation, what we get? y1 plus z1 whole square equals to, take this term to right side, minus times 2x1 minus 3y1 whole square, and this implies taking square root, what we get? y1 plus z1 equals to under root of minus 2x1 minus 3y1 whole square. Okay, and this is nothing but equals to under root of minus 1, what will we get? I. So I times under root of 2x1 minus 3y1 whole square, that is 2x1 minus 3y1. Okay, so y1 plus z1 equals to I times 2x1 minus 3y1. Similarly, by second equation, for first equation we get y1 plus z1 equals to I times 2x1 minus 3y1. So similarly for second equation we get y2 plus z2 equals to I times 2x2 minus 3y2. Okay, so y1 plus z1 equals to I times 2x1 minus 3y1, and y2 plus z2 equals to I times 2x2 minus 3y2. Now using these two, we get, this implies 2 times y1 plus z1 into y2 plus z2 equals to 2 times y1 plus z1. So 2 times, okay, I into 2x1 minus 3y1 into I into 2x2 minus 3y2. I into I is I square is minus 1. So here minus sign, minus 2 times 2x1 minus 3y1 into 2x2 minus 3y2, and taking this to the left hand side, we get, taking this to the left hand side, so this minus 2 will become plus 2. So what we get? Plus 2 times this equals to 0. So we have obtained this, and using this equation hash implies this sum equals to 0. So this sum equals to 0. What is left hand side? This. So this sum equals to 0. And as this sum equals to 0, that means this element satisfies this condition. So this element belongs to A. That means sum of these two vectors belongs to A. And so as these two vectors are arbitrary, so we see that A is closed with respect to vector addition. That is, we have proved the first condition of our subspace test. Now we have to prove that A is closed with respect to scalar multiplication as well. So let's prove it. Now let's prove that A is closed with respect to scalar multiplication as well. So to prove that A is closed with respect to scalar multiplication, we need to show that alpha times x, y, z, alpha times this element belongs to A for every x, y, z, order triplet x, y, z belongs to A, and for every alpha belongs to F. Now, as x, y, z, this triplet belongs to A, so this triplet must satisfy this condition. So from this we have this element belongs to A, so this element must satisfy this condition, that is y1 plus y plus z, because this is x, y, z, y plus z whole square plus 2x minus 3y whole square equals to 0. Give this as equation $. Okay. Now this equation, we have this equation from here, this condition. Now we have to show that this element belongs to A. So this element must satisfy this condition. Okay. To show that this element belongs to A, we need to show that this element must satisfy this condition. So let's consider second coordinate plus third coordinate whole square. Second coordinate plus third coordinate whole square plus 2 times first coordinate, 2 times alpha x minus 3 times second coordinate alpha y whole square. Is this sum equals to 0? If this sum equals to 0, then this element belongs to A, and so A will be closed with respect to scalar multiplication. Now this sum I can take common. What we get? Alpha square times y plus z whole square plus alpha common. What we get? 2x minus 3y whole square. Sorry, alpha square, because it is a square term. So when we take alpha common, outside will be alpha square. So alpha square in bracket y plus z whole square plus 2x minus 3y whole square, and this is equals to alpha square. This sum equals to 0 by this equation. So this is 0, and so this sum overall equals to 0. So this sum equals to 0. That implies this element satisfies this condition. As this element satisfies this condition, so this element belongs to A, and so A will be closed with respect to scalar multiplication as well. And earlier we have proved that A is closed with respect to vector addition, and here A is closed with respect to scalar multiplication. So combinedly, by subspace test, we have A is a subspace. This shows that A is a subspace of real vector space R3. So option A is true. That is, answer to this question is option A. So if you enjoy this video, please like and share this video and subscribe to our YouTube channel. Thank you for watching.